All right, everyone. Here is our kind of notes discussion for the day. So, we're going to actually start to get into what is this force at a distance thing that we have been talking about. This, thing that applies to objects with shape. So, the name of this thing that we have been talking about is torque. And I always share that my sister had a college professor who had a slight accent and therefore pronounced this word twerk. But it is torque. Okay. So torque is kind of what we've been dancing around, what we've been talking about. When we were lifting our tracks up, we were balancing the torque from the force of gravity and the torque applied by the tension. And since they were balanced, they were equal, which is why we could set the slope of our graph equal to the force and distance of the gravity. So, kind of what we saw in the lab and what we kind of also kind of fundamentally know to be true just by existing in the world is that if we apply a force from a distance of an axis of rotation, we can cause a rotation. And so that specific force at that distance is called torque. So torque is a force applied at a distance from an axis of rotation that can cause rotation. Now I say can cause instead of does cause because sometimes we have balanced torques, and that's what we're going to kind of focus on first is what our torques are balanced. So our object is not rotating, it's remaining at rest. So let's think about a door to think about what else we need to kind of consider with this thing torque. So here are my hinges on the door, right? And here's my doorknob. Now, I'm sure you have tried to open doors before. You had to open a door to get into this classroom. You probably opened many doors, right? So you know, likely, that when you try to push close to the hinges, you have to apply a really, really big force to open that door. Whereas if you apply a force to the doorknob, you don't have to apply as much force. Right? And if you apply in the middle, you have to kind of apply a very medium amount of force. Okay? So what this is showing us is that the further we get from these hinges, the less force we have to apply. And we saw that with the track lab as well. Okay, let me try and draw a track here. The further our string was from the axis of rotation, or the foot, the less tension force we needed to apply. So we're seeing this inverse relationship between force and distance from the axis of rotation. So essentially what that means is they need to be on that force is proportional to 1 over r, or if they're on the same side of the equation, force times r should be in our equation. Right? So that's true for pretty much anything you've ever thought to try and rotate. The further away you are from that axis of rotation, the easier it is to rotate it, right? That's why if we're picking up, say, like a board that's on the ground, right? And we kind of use this end as a pivot point. We keep this end on the ground. It's easier to lift the board from this complete opposite end than it is to try to lift the board in the center because we have this inverse relationship between force and R. Okay. So we see that as the distance from the axis of rotation increases, the force needed decreases. Okay. Now, let's get back to our door. Okay. Not all forces that we push on a door with can actually rotate the door. So think about like your bedroom door, not necessarily the classroom door because that has a spring mechanism, but think about a door that's just like able to swing back and forth with no issues, right? Now, you can probably think about some situations where you can apply a force to the door, but the door actually doesn't rotate. So some of those situations might be if we pressed on the edge of the door like this or pulled on the edge of the door, right? I can push and pull on that edge of the door all I want, but that's not going to cause a rotation. Similarly, if I apply a force down on the top of the door or apply a force up from the bottom of the door, no matter where I try to do that, I'm not going to rotate the door, right? The only way I can rotate the door is if I apply a force kind of along this squiggly line. With one exception, though. If I apply a force right on the hinges of the door, that's also not going to cause any rotation. So that's why I'm drawing these forces in red, signifying that they don't cause any rotation. Okay. So that's kind of going to tell me a few things. This part here tells me that if I'm at the axis of rotation, if my force is at the axis of rotation, we cause no torque. Okay. This here tells me that the direction I apply my force might matter. So let's think about how we pull on a doorknob, right? Usually we pull on a doorknob nice and perpendicular to that doorknob. Think about trying to open a door by pulling not perpendicular to the doorknob, like kind of stepping to the side of the doorknob and trying to open it, right? My guess is this force, you're going to have to apply a little bit more force to open the door than if you apply perpendicularly. So again, this is telling me that the direction I apply the force matters, and that the easiest way to apply the force is kind of perpendicular to the door. So that tells me that 90 degrees might be an angle of interest, right? Might result in a maximum, right? So again, this is telling us that the angle at which the force applies matters. And the easiest for opening a door, at least, easiest is at 90 degrees. Okay. So now that we've kind of figured a couple of things out, it's time to actually introduce the equation for torque. So the equation for torque, or the variable for torque rather, is the Greek letter tau, right? It's kind of like a backwards J, but that's how we represent torque. And yes, torque is measured in Newton times meters. So we calculate a torque by doing a force, which is measured in newtons, times an R, which represents the distance from the axis of rotation, right, which is in meters. So that takes into account this part because that gives us that inverse relationship. And then to take into the part with the angle, since we know we need like a maximum or a best at 90, I need to pick the trig function that allows for a maximum at 90. And that's going to be the sine of theta. So that's why we stick on a sine of theta. And this is the angle between, F and R. So let's go back to our door and make sure this equation makes sense with the door, right? So no matter what, we're going to have to apply the same torque to the door to open it, right? It needs the same force at a distance to open the door, right? That's this, the door stays the same weight, the hinges act the same way. Okay, so let's see. As I increase this R value, and this torque has to stay the same, F can decrease, supporting why we need the doorknob at the furthest end from the hinges. That's why we don't have doorknobs in the middle of our doors, right? Because if we have the door as far away from our axis of rotation, we're maximizing that R so we can minimize that force F. All right. Now, with the hinges, if I apply a force at the hinges are where I'm rotating. So the hinges are where I have an axis of rotation. So that makes my R value 0. And if my R value is 0, then my torque value is 0, which explains why we see no rotation when I apply a force directly at the hinges. So again, this equation makes sense. Now let's think about the angle, right? When I applied this force, right, this angle is between F and R. And you might be like, what? R? How? So we can draw an R vector from with the axis of rotation to the point where the force acts. So this would kind of be like my R vector. So the angle between those two is 180. Right? Now the sine of 180 is 0. So that again gives me a 0 on this right-hand side, which is going to give me a 0 on this left-hand side, which is why this force applied pushing on the edge of the door does not create a torque. Okay? And then our last example, when we apply a force perpendicular to a doorknob, the sine or the angle is 90 degrees. I have 90 degrees between this green R vector and this F. Right? So sine of 90 is 1, and that's the maximum value of sine. So this force F has an angle of, I don't know, theta, but it's something less than 90. So this sine value is going to be something less than 90. It's going to be less than maximum. Right? Now remember, I have to apply the same torque to the door, and I can't change R. So that means the force I have to apply has to increase, which is why we don't open or close doors from the side. Right? That's why we open or close them perpendicularly. Okay. So this F, right? I got to get my black pen back. Okay. Now, the way that this torque equation can be read is we can either kind of think of F sine theta times R, where this is the perpendicular component of the force, which is usually what we use. We talk about the perpendicular component of the force. Or it can be thought of as R sine theta F, right? This R sine theta would be the perpendicular component of the distance from the axis of rotation. And that's also called the lever arm. Now, we don't usually solve problems like this, but it does come up in the concept builder, so I wanted to kind of talk about that. The perpendicular component of the force should be relatively easy for you guys to remember or understand, right? So if I have a force F and this is my R, the perpendicular component would be this component, right? The force that's perpendicular to the radius. Okay. The lever arm gets a little bit more confusing. Okay. So if I have, I don't know, some sort of door and I'm applying a force perpendicular to that door, the perpendicular R is nice and easy, right? It's just along the axis of the door. Okay. But if I apply a force not perpendicular, right, then my lever arm looks something like this, right? So this would be considered like the hypotenuse of R, and this would be considered R perpendicular. So it's perpendicular to what's called sometimes the line of action, which is that dashed line that I drew, which is in the same plane of the force. Again, we normally kind of talk about like F perpendicular because I think that that makes a lot more sense, but it comes up in the concept builders with this idea of lever arm, which kind of takes into account, instead of the perpendicular component of the force, the perpendicular component of the radius. So it kind of changes our coordinate system from being like in the plane of the door to in the plane of the force, right? Which is why R needs components. Okay. So that is our torque equation. And that's what we're going to be kind of working on for the next couple of weeks. So for today, you guys are just going to continue on kind of the basics of torque, ranking torque, identifying which is larger. And then what you're also going to get into is whether a torque or the total torque is balanced or unbalanced. So you'll be presented with a balance beam of sorts on a fulcrum. And since we have an obvious point of rotation, that's going to be our axis of rotation, right? And you will have like masses on either side. So if I have a mass on this side, right, that is going to apply a force downwards on this balance beam. That force is going to cause this balance beam to rotate this way, right? And we call that direction of rotation clockwise, right? So in the same direction as the clock. Now, let's say I put another mass of the same value, but closer to the axis of rotation, right? If it was just that mass alone would create a counter clockwise rotation. Okay. But if I had both on here, I would need to figure out how do the torques compare to each other? And does that total torque create a clockwise or counterclockwise or no rotation, right? That would mean the torques were balanced. So to think about that, I need to know, right? Let's call this 2x, right? I would need to know the torque from this side, which the torque would be the force times the distance from the axis of rotation. And these are both perpendicular, so I'm not going to worry about sine theta. So this is producing a torque of Fx. This side is producing a torque of 2Fx because it is twice the distance away. So since these torques are not equal, this system is not going to be balanced and it's going to rotate in the direction of the larger torque. So this system would rotate clockwise. And we say that that causes an angular rotation, right? Or an angular acceleration, I should say. Now, for this unit, we are going to use the convention that counterclockwise is positive and clockwise is negative. Now, you might think that using counterclockwise as positive is counterintuitive. So funny. Because it kind of is. It does feel a little bit backwards. But if you think about it in terms of math class, it actually makes sense. Because in math class, when we're talking about angles, we set the x-axis as 0 degrees, right? That's 0 degrees. And then when we want to measure angles, we open up and form angles clockwise relative to the x-axis, right? That's the direction of our positive angles. And I said clockwise, but I meant counterclockwise. That's the direction of our positive angles. The directions of our negative angles is clockwise, right? So what we're doing is actually following the same conventions that you guys do in math class, where counterclockwise is positive, clockwise is negative. So that's the basics of torque. You guys are going to continue on with those 3 concept builders that I assigned. Start with the one that's called torque, and then you're going to do one about balanced and unbalanced. And then I forget the name of the third one. Let me check real quick. Getting a handle on torque. And that's the one where I think you're going to identify counterclockwise versus clockwise. You are more than welcome to work with other people. If you do not have a laptop, you can, of course, use your phone. These are going to be due next week, but please use the class time to do these wisely. I'm going to be really upset if it comes next week and there's still people who haven't finished these, because you guys will have a good chunk of time to get these done in class. So please be productive, keep working, and then tomorrow we're going to do some problem solving with keeping things balanced and calculating torques for situations where we are not rotating and we have balanced torques. We're going to get into some more complex problem solving. Okay. So that is it for today. Again, refer back to this stuff as you need for the concept builders. And that is it, I believe. Okay, I'll see you tomorrow.